So this is the video for FIQ2. So we have the situation here is we have a coin that weighs 0.005 kilograms, and it's placed on this rotating disc, and it's placed 0.14 meters from the center. So and we are also told that the coin does not slip, and that the time it takes for the coin to spin to make a complete revolution is 1.5 seconds. I've labeled the given values here. So the mass of the coin is 0.005 kilograms, and then I called this length r because for this problem we're just going to think of the circle as the distance that the coin actually goes around, based on how far it is from the center, not how big the plate is. And then t, the big T is period. The period, so how long it takes for the coin to make one revolution. So knowing that, the first question is question A. It asks, the figure below shows the disc and coin as viewed from above. Draw and label vectors on the figure below to show the instantaneous acceleration and linear velocity vectors for the coin when it is at the position shown. So they're asking for for vectors that represent acceleration and velocity. So, well, since the object is moving in a circle and it's not slipping, there is some sort of force pulling the coin in towards the center of the circle, and that can be referred to as the centripetal acceleration. So since the centripetal acceleration is what keeps the coin pulling towards the center, I think it's safe to say that the vector pointing towards the center would be acceleration, because that's what's pulling. Acceleration should be pointed towards the center of the circle at all times, because that's what's making sure the coin doesn't fly out from the disc. And then velocity should be tangent to the circle, so sort of like that, because the velocity of the coin should always just be kind of going forward, but it's because of the centripetal acceleration that it's always like going towards the direction where the disc is moving. The acceleration is what's changing the velocity bit by bit. Okay, so that's question A. And the second question is B, and it asks for the speed of the coin. So speed basically just equals the absolute value of velocity. And to get that, I'm going to use the equation T equals 2 pi r over v. Now, the reason why I use this is because T is the period, which is in seconds, and that's a given. And 2 pi over r, that's the formula for circumference. So that's essentially the distance that the coin travels. So we have, I'm gonna just rewrite this with different variables. So we're gonna have delta x here equals t delta x over v. So we have the delta x, how far it's traveling, and v, which is velocity. So if we think about this, if we think about this unit-wise, this would be seconds equals meters divided by meters per second. So these would cancel out, and we'd be left with seconds equals seconds. So we know the units work. but it also works because if we know how long it takes for the object to move a certain distance, and we know the distance, then we know how fast the object moved based on the distance and the amount of time it took, which is what we just saw there. So let's plug in the numbers. So t equals 1.5 seconds, 2 pi r, which is 0.14 meters over v. So to isolate v, we can just cross multiply. And this comes out to be 0.59 meters per second. So that's the velocity of that's the speed, technically, of the coin. So that answers part B. Part C says the rate of rotation of the disc is gradually increased. The coefficient of static friction between the coin and the disc is 0.5. Determine the linear speed of the coin when it just begins to slip. So now we are given the coefficient of static friction is 0.50. Cool. So if we draw a free body diagram of the coin, kind of from like from a direct view, if this is the coin flat like that, we obviously have the centripetal force, which is, in this case, is just friction, because that's what's keeping the coin from slipping off. Then we have the normal force of the disc pushing back on the coin. And then we have mg. So yeah, if we do Newton's second law, we can write F equals force of friction equals ma, and then we can substitute these because we know a, in this case, is centripetal acceleration, and centripetal acceleration is just equal to v squared over r. So that means we can substitute this for mv squared over r. And then force of friction is just coefficient of static friction times mg. So we set this equal to, we set the centripetal force equal to friction because we want to know basically the fastest speed that the coin can go without slipping off. So that means we have to set v equal to whatever this is. So yeah, we can start to isolate v. Off rip, we can cancel out the m's. Then we can just multiply by r on both sides, and then we can square root it. And now we have all the known values that we need, so we can do so 0.14 times 0.5 times g, and that number is 0.83 meters per second. Sorry, my handwriting is not the best. So yeah, that is the linear speed of the coin when it just begins to slip. So yeah, so that was part C. So then, last question D. It gives a hypothetical scenario where it says, if the experiment in part C were repeated with a second identical coin glued to the top of the first coin, how would this affect the answer to part C? Explain your reasoning. So basically, they're just saying they would like double the mass of the coin. So instead of 0.05, instead of 0.005, new mass, I'm gonna say mass sub n, would be 0.010 kilograms. So how would it change with this new mass? How would the maximum speed change with a coin? Well, to figure this out, we can set the frictional force equal to the centripetal force again. And if we plug in friction again, it's just static friction times normal force. And so how would a double the mass change? Well, it wouldn't change anything, because like we did in the earlier step, what we did was just cancel out mass. So the new equation was just this: static friction times gravity equals v squared over r, or the centripetal acceleration. So yeah, I mean, mass doesn't affect the acceleration, because it just gets canceled out in the first step. Yeah. So mass shouldn't really affect the velocity of the coin, since if the disk continues to keep going the same way, and as long as the coefficient of friction also stays the same, and yeah, the radius stays the same as well. So yeah, nothing, the mass should not affect how fast the coin has to go in order to start slipping off. So yeah, that was the answer to part D, and that was the end of the FRQ. So yeah.